This course has taken us from an introduction to the life science industries to a detailed look at drug discovery and the regulatory issues that affect that process, and then an examination of research and testing laboratories along with the types of technologies that are found in them. Now we will begin to look at some of the instrumentation that laboratories use in their work. We are going to take a look at one instrumental technique in some depth. That technique is called chromatography. It is one of the most popular and useful techniques in the life science industries and found in most laboratories whether they are doing research or testing. It's also widely used in other industries including chemistry, environmental sciences, and other laboratories outside the life sciences. Because of its popularity, it has been a target of computer-based automation efforts since the 1970s. It provides a good illustration of how automation has been developed and applied, and provides a good model for understanding automation as it is used with other laboratory equipment. Most laboratory analysis work is best done when you're using pure compounds. When working with mixtures, one chemical can interfere with the analysis of another. It is a bit like looking at a stack of transparencies and trying to figure out what is on each one of them without separating them. When we are viewing transparencies, they can be separated by hand and viewed individually to see what is on them. When we are looking at chemical compounds in a mixture, we need a tool to separate them. Chromatography provides that separation tool and solves a major problem. Chromatography analysis is fast and can complete many tests in a few minutes. Some tests with very complex mixtures can take up to an hour. It has wide application in a variety of industries, including the petroleum industry, where it is used to carry out simulated distillations, and in the plastics industry, where it is used to look at the molecular weight distribution of plastic materials. We are going to begin by looking at how chromatography works, then take a look at how an instrument is put together, and finally, look at how automation has been used to make the technique faster with less reliance on people. The picture on the screen is that of a wind-powered vehicle that can move at speeds of over 100 miles an hour on a dry lake bed. In the 1860s, less sophisticated vehicles were used to travel across the Kansas prairie. These were referred to as wind wagons. Imagine two types of wind wagons, both of the same size and weight, but with differing diameter wheels. Also imagine them running a race along the straight path over a rough surface. At the top of the diagram we see both the large-wheeled and small-wheeled vehicles mixed together at the starting line of the race. Once they start, the larger-wheeled vehicles pull ahead because they can move over the rough ground much easier. The small-wheeled vehicles get caught in ruts and don't move as quickly. This is the basic principle that is used in chromatography. Different chemical compounds interact with the separation materials differently, and as a result move at different speeds when pushed through them. There are a number of types of chromatography, and we will begin by looking at one called thin layer chromatography. A stiff sheet of mylar is coated with a powder, in this case silica gel, the same material that is used as a drying agent. The silica gel acts like the rough surface in our wind wagon race. The mixtures of chemicals we want to separate is lined up as a series of dots along the bottom of the sheet as shown in the diagram on the left. We will place the bottom end of the sheet in a solvent called acetone. It does the same job as the wind in our race. It moves the material along the sheet. In practice, the sheet stands in a jar, as shown in the diagram on the right, with the bottom end the solvent and the jar covered to prevent the solvent from evaporating. This series of images shows what happens to one of those spots as the solvent moves higher on the sheet. The solvent darkens the sheet as it moves up. As it does, what started off as a dark line separates into a series of colored bands. The separation took about 9 seconds. It's a good demonstration of how chromatography actually works. This slide shows another thin layer chromatography analysis, using different amounts of the same material. As you can see, the more material that is present in each band, the more intense the color. Now we are going to isolate one of those test strips and look at it in more detail. We converted the color image to a grayscale image and then scanned it to take a look at the intensity of the individual bands. The scan shows a series of individual peaks, beginning with one very large peak on the left, and then a series of smaller peaks as we go from left to right. These match what we see with our eyes on the test strip. The distance that a chemical moves over time, in this case beginning at the left and moving towards the right, is characteristic of that material and is referred to as retention time or retention index. That value can be used to determine what the chemical is. This is referred to as qualitative analysis. The chromatograph's ability to identify chemicals is done by comparing the retention times of a peak to known compounds. It is possible for more than one compound to have the same retention times, so that if a positive ID is needed, other analysis techniques will have to be used to confirm the match. Part of the analyst's job in setting up the analysis is to develop a set of conditions in which all expected compounds in a sample are separated from each other. Interferences, unexpected chemicals, can pop up, and when they do, the analyst may rerun the analysis with a different set of conditions to avoid the problem. The ability to identify compounds and see what components are in a mixture is illustrated by these two images. What they show is a thin layer chromatography of different types of inks. The names of the inks are shown on the bottom. Those in the diagram on the left are from the Sharpie red pen, and the ones on the right are from a red pen of a different manufacturer. The same holds true for the black inks on the right image. In both cases, you can see that some colored bands show up in one type of pen and not in another. For example, in the black inks and the two streaks on the right contain blue compounds that aren't found in the black Sharpie's ink. If we measure the size of the peak, we will have an estimate of the amount of material that's there. This is called quantitative analysis. Chromatography provides the ability to determine what materials are and how much is present in a mixture. As a result, it's a very powerful and useful technique. While useful, thin layer chromatography is not very practical for production environments. The process of setting up, spotting samples, and making measurements is very slow. In order to be useful in a productive environment, we need to change a few things. Suppose we took that thin layer plate, rolled it into a tube, and filled it up with the material that was used to make the separations possible. In the examples we've been using, that material would be the silica gel. We would then have a chromatography column. Several of them are shown in this photograph, and they come in different lengths depending upon the kinds of separations you're trying to achieve. In our thin layer chromatography example, we simply stood the plate in the solvent to start the separation process. When we use chromatographic columns, we have to move the solvent into the column differently. What we use is a solvent pump that pushes the solvent through the column to carry out the separations. Samples are injected into one end of the column, not too differently from the idea of spotting them on a plate, and a separation takes place as the solvent moves through the column. In a thin layer plate example, we use colored materials so that it would be easy to see the separations taking place. In production work, we need a different approach. Instead of using our eyes as a detector, we use an electronic device to sense the chemicals coming out of the column. The computer system connected to the detector keeps track of the amount of material coming out and forms the peaks that we use for measurements. In the thin layer example, some of the materials we placed on the plate didn't move away from the position they were in when we spotted them. If we let that happen on the chromatographic columns, the system would get blocked up and affect the analysis. In a technique called liquid chromatography, which is basically what we've been describing, we can use a mixture of solvents instead of just one solvent to move the materials through the column. This allows us to analyze a wide range of materials and increase the power of the technique. The technique is called liquid chromatography because the solvent used to move the material through the column is a liquid. There are other types of chromatography, such as gas chromatography, where a gas such as helium or hydrogen is passed through the column. Liquid chromatography is the dominant type in life sciences. A liquid chromatograph is a sophisticated device. The illustration on the screen shows a modern instrument with some of the components labeled. The solvents are managed by devices near the bottom left of the unit. The column chamber that holds chromatographic columns is shown on the right, and the detectors at the top of the unit. A computer system is used to control the chromatograph and collect the data. Modern systems take extensive advantage of computer technology. That wasn't always the case. This is a 1965 photograph showing a gas chromatograph in use. The column chamber is labeled, and the section below it contains all of the control electronics, consisting of dials and gauges, all analog electronics with no digital systems. Samples were injected into the instrument using a syringe that was inserted into an injection port. It's enlarged in the inset but difficult to see. The injection port was heated to evaporate the samples, and they were carried into the system as a result of the movement of gas through the columns. The detector signal was shown as a pen trace on a strip chart recorder. The colored image shows a type of output that would normally be seen from the detector. Samples were injected manually one at a time, and the output could have taken up hundreds of feet of strip chart paper that had to be analyzed manually. The images you see on the screen are the detector output from more modern instrumentation. Notice the time scale on the bottom. One instrument completes the analysis in a little over 6 minutes, where the other takes 25. If you are an analyst doing this work manually, you would be sitting in front of the instrument doing an injection every few minutes. If the analysis time were long enough, you could get up and do something else in between injections. In many cases, the analysis was too short, and you just sat there all day doing injections. The result was a less than effective use of people's time. But in 1965, there wasn't any alternative. Modern equipment can take advantage of auto-injectors, otherwise known as auto-samplers, that can automatically pick up samples from a rack and inject them one at a time. The image on the screen shows an auto-sampler sitting on top of a chromatograph. The racks of blue circles are actually sample vials that have been set up for analysis. The injector will automatically pick up these tubes out of the racks and place them on circular carousels. Carousels will rotate samples into position under the injector, and the unit will take a sample out of the vial and inject it into the instrument. Auto-injectors can take many forms. The image on the bottom left shows a vial being extracted and getting ready for injection. The image at the top left shows a different style of auto-injector with the samples that are laid out in a carousel instead of racks. The image on the right shows an interesting development in auto-injectors. This is a network system developed by Baytech International called the turbo tube. Roughly in the center of the diagram, you see a rectangle identified as a sample bank. This is a centralized sample repository where sample preparation can be done. Samples are then sent through pneumatic tubes to sample routers, which supply them to each instrument. In the diagram, they are labeled as GC for gas chromatograph. The pneumatic tubes can be hundreds of feet long. This arrangement allows for centralized sample management and preparation, which can be of considerable advantage if you're working with hazardous materials. These systems are an example of specialized robotics. The following video clip shows the system in use. Note, the use of a vendor product should not be taken as an endorsement. They were just kind enough to let us use their video. Before we get to the video, we want to spend a few minutes setting the stage. The whole point of the injection process, which the autosampler is designed to facilitate, is to get samples into the instrument. Prior to this, the analyst would have prepared the samples. One common method is dissolving them in a solvent. Additional steps might be needed depending upon the nature of the material. A portion of the prepared sample is withdrawn from the sample container with a syringe and injected into the instrument's injection port. This work may be done manually for a few samples, but when we start getting into dozens or more, an autosampler is a more efficient way of doing it and allows people to do more productive work. This slide shows the device you'll see in the video with the major components labeled. Each rack contains 50 samples that are moved into the carousel where they are injected into the instrument using a syringe.
The self-aligning plug-and-play injector mounts in seconds without tools. It can be easily moved from one inlet to another, or quickly and easily transferred between GCs when workloads change. The lightweight removable design also permits easy maintenance. In addition to conventional and fast injection modes, the 7693A ALS system offers pre-injection sample handling capabilities that can further enhance your lab's flexibility, productivity, and performance. Ideal for routine sample handling in a wide range of industries and applications, including forensics, food and environmental analysis, this can often eliminate or minimize separate sample prep work, saving both time and resources. In addition to the time-saving capabilities of the 7693A ALS system, there are important health, safety, and economic benefits. Since manual handling of samples is reduced, there's less exposure to harmful chemicals. Labs may also scale solvent usage down by 90% or more, thereby decreasing both solvent and waste expense.
The video clip talks about the ability to make adjustments to the samples that are being prepared for injection. They can be heated, stirred, diluted, and so on. This is a considerable advance over work that we may have done a decade ago, which could have required the development of specialized robotic systems that could have taken months to put together. The previous slides addressed the problem of getting the samples into the instrument. We also have to deal with the analysis of the data. The first step in an analysis is to develop a calibration curve based on known samples. The curve can be used to translate the size of the peak into a result. Analyzing the data from a number of chromatographic runs can take hours. That problem was solved by the development of the chromatographic data station, which consisted of a computer system that would automatically collect the data and perform the peak detection, construction of the calibration curve, and sample analysis. With the combination of devices we've looked at, we can see an example of an instrument workflow model that is repeated for most instrumentation that you'll find in life science laboratories. The process begins with sample preparation, moves on to introducing the sample into the instrument, with the output of the instrument being collected by a computer system that does the analysis, reporting, and data storage. The computer system and sample injection system have to be synchronized so that both agree on when a sample is being introduced and data collection for that sample can begin. Depending on how things are set up, either the sample introduction system or the computer can be the master control device. In practice, it makes more sense for the computer system to act as a controller, particularly if it's going to be linked to other data systems. When we look at other instrumentation, we'll see this model repeated. This instrument workflow model can be implemented with equipment from a variety of vendors. The instrument itself, the robotic sample preparation system, plate handling systems that are common in life sciences, and computer systems can be purchased from one vendor or from systems integrators. This approach can cause problems when developing automated systems. Each vendor has a core technology that they work with and sees themselves as the center of the automation universe. Vendors will offer add-on products built around their core technologies. Those add-ons are designed to improve product operations, its marketability, and add capabilities that customers request. Often, those add-ons will be done to improve third-party access, because customers are demanding improved connectivity between a given product and other products that they're using in their labs. These changes may also be needed due to competitive pressures that were not foreseen in the development of the core product. This interaction with third parties in some cases reflects a vendor's focus on the core product, using third-party connections to solve technical and marketing issues that they don't want to address themselves. Products come from both large and small vendors, and each has its own approach to dealing with integration issues. Small vendors will concentrate on their core product and technology. In many cases, they simply don't have the funds or capacity to move beyond their initial market, at least until the product proves itself and generates a revenue stream. They could be a 1 or 2 person operation. In their view, the quality of the science comes first. If the equipment doesn't do the science properly, you get a bad reputation, and the company will fail. In many cases, the equipment is very specialized, and a lot of work goes into developing products for very narrow markets. Product aesthetics is secondary to functionality and getting the science right. Money is spent on the essentials. For small instrument vendors, once they prove a means of collecting data from the device, they see their job as being done. Working with the data is up to the user. Anything outside the vendor's primary sphere of interest is usually addressed by using a simple export format such as Excel, with detailed analysis left to the user's discretion. Larger vendors can afford to be more sophisticated, since they have larger engineering organizations and budgets that allow more freedom of movement in product development. Competition will force ease of use issues, with customers looking for the least complex product to carry out functions. Large vendors at one time were small vendors and probably established their reputations in the early days of their development. As a result, their name will command more attention by the press and lead to faster development of the revenue stream. When they develop data systems, they exert control of the data being used in proprietary formats and only export information in simple formats. In their view, third parties have to integrate with them, and it puts them in a controlled situation. We saw this pattern of development play out in the development of data stations for chromatography systems. The data stations initially came in two forms: dedicated integrators and multi-user, multi-instrument software systems. When integrators first came on the market, they had very limited functionality. Many were marketed by the companies that made the chromatographs, the core of their business, and they provided the minimum functionality the vendor thought the user needed. They could detect peaks coming out of the detector, measure the size of the peak, and report that information plus retention time for each peak. The rest was left to the user. The information was printed out on a strip of paper and had an RS-232 port for communications. As the customer base began working with them, the users demanded more functionality. The data systems began carrying out more of the workload, including the development of calibration curves and final results for chromatographic information. Other vendors who had a better understanding of computer systems developed multi-instrument, multi-user systems that provided more complex calculations, database capability, and the potential for linking the systems through networks. Both the chromatography and computer vendors saw the world of data acquisition and processing differently because the centers of their product universes differed. One focused on the instrument, the other on computational issues. Eventually, the systems improved their ability to connect the instruments by using networked interface boxes, which in reality were dedicated computer instrument interface systems. This relieved the need to have a host, general-purpose, multitasking computer system tied directly to the instrument and solve problems that occur when a shared system is doing real-time analog to digital data acquisition. This made the results more reliable, since it also reduced electrical noise during data acquisition. The old-style data integrators have largely left the marketplace to computer systems that either tie directly to the instrument or to more sophisticated client-server systems that allow multiple instruments to be managed by a single software system, providing more capability than previous systems offered. These systems have some basic core functions that are common to any instrument data system. They provide data acquisition, the ability to control or respond to an autosampler, peak detection, baseline correction, the ability to perform complex calculations, reporting and display of information including chromatograms, and data storage. Client-server systems, because of their need to support multiple analysts and samples, required the addition of management functions similar to those found in laboratory information management systems. That includes the ability to log samples in so that each sample and the data associated with it has a unique ID, search functions, and the ability to generate work lists, instrument maintenance functions that support regulatory control, and more extensive reporting and results management. These systems are sufficiently sophisticated that for laboratories that are dedicated to just chromatography, they may provide a complete solution to the laboratory's needs. So far, we've looked at chromatography in depth because it is a good example of how automation developed to support an instrument and how it can be applied to a particular technique. Chromatography is a widely used technique for both testing and research applications and is often used in conjunction with other instrumentation, as we'll see later in this section. We've also looked at vendor concerns at how different vendors, depending on their size, approach the marketplace. We are now going to move on to other instruments and techniques, and for the most part in much less detail than we did with chromatography. This is the workflow model that we've illustrated so far, and understanding it is important to laboratory work. The instrumentation we will look at works within this model. Sample preparation is a necessary step for instrumental analysis, and for the most part follows a similar pattern to that covered in chromatography. So we'll omit a discussion of it for most of the techniques and simply assume it's being managed. Most instruments today are purchased with data systems to control them. In some cases they are part of the instrument package, in others they are purchased from another vendor. We are going to begin by looking at some techniques that examine samples with light. Light is a form of electromagnetic radiation that includes gamma rays, X-rays, microwave, and radio emissions. We view this light as it comes in three forms: ultraviolet, visible, and infrared light. Each of these affects chemical compounds in different ways depending on their structure. Because of the way it interacts with organic molecules, such as those found in life science applications, ultraviolet spectrophotometry can be used to study proteins, enzymes, and other molecules of interest to researchers. Visible light, which is made up of a range of colors that we can see, can be used in certain types of quantitative analysis that we'll look at later on. Both ultraviolet and visible spectrophotometry can be used to measure the amount of a compound in a mixture or solution, and as a result both are useful in quantitative analysis. They are not particularly useful to determining the structure of molecules. Infrared spectrophotometry operates at wavelengths that interact with the structure of organic molecules, and as a result can be used to identify chemicals, give information about their structure, and also be used for quantitative analysis. It works best when you're working with pure materials. We are going to look at ultraviolet and visible spectrophotometry together, since both have some similar characteristics. Both can be used for quantitative analysis, and the spectra they produce is fairly simple. The diagram on the right is an ultraviolet spectra of a chemical called isoprene. The structure shows that the compound is made of carbon and hydrogen atoms. Notice that between the two pairs of carbon atoms there are double lines. Those lines are the reason for the peak on the left side of the chart. Because of the simplicity of the spectrum, this technique, in this case ultraviolet spectrophotometry, can be used for determining how much material is present in a solution. Just as we saw in chromatography, the analyst would run a series of standards that would tell him how the size of the peak relates to the amount of material in solution, and give him the information needed to create a calibration curve. When the samples are running, the analyst can compare their peak heights against the calibration curve and read the concentration. This allows for simple and rapid analysis. One issue that occurs in the study of organic molecules is their stability in solution. By repeatedly scanning the same solution over a period of time, we can watch how the size of the peak changes and get a direct measure of the rate of breakdown of the chemical over time. Another use for ultraviolet wavelengths is to use them as a detector in chromatography. We can set the detector for a specific wavelength and make it easier to detect materials coming out of the chromatographic column. Visible spectrophotometry can be used in the same way for quantitative analysis. Another type of spectrophotometry is done by measuring light in the infrared wavelengths. This technique allows for both qualitative and quantitative analysis. When we're dealing with pure or nearly pure compounds, we can use the spectra to determine the structure of the chemicals we're looking at and provide a positive identification for them. We can also use the size of the peaks to determine how much material is present in a solution, just as we did on the last slide. The image you see on the screen is an infrared spectrophotometer. It doesn't look very impressive because most of the controls are now digital and the system is managed by a separate computer system. The gray section in the middle is a sample chamber, and the black device sitting on top of the unit is a sample holder. The infrared beam would pass through a sample in the circular opening near the top of the holder. The model on the upper left corner of the screen is that of methane, an organic compound made of one carbon atom and 4 hydrogen atoms. In reality, the molecule and atoms are constantly vibrating and bending, and these motions are detected by the infrared spectrophotometer and show up in specific places when we record the infrared spectra. For example, the green line on the chart shows a region in the spectra where atoms are either bending back and forth toward each other or stretching away from the central carbon atom. The spectrum on the upper left is that of methane, and it is unique to that chemical compound. The peaks on the left, around 3,000 wave numbers, are caused by the carbon and hydrogen atoms stretching away from each other. The peaks on the right are caused by pairs of hydrogen atoms bending back and forth with respect to the central carbon atom. The infrared spectra of different chemical compounds is unique for each of them and can be used to identify them. If you watch police TV shows such as NCIS, Bones, or the CSI series, or similar shows that have laboratory work as part of the action, they may reference a device called a mass spectrometer. This device helps scientists determine the structure of a chemical compound, and as a result does qualitative analysis. It works best when it is dealing with pure compounds, but it can be useful in the analysis of mixtures of materials. One of the problems in dealing with large molecules such as proteins is figuring out what their structure is. The mass spectrometer approaches it by breaking the molecule into pieces and allowing the analyst to figure out what the pieces are. They can then go back and figure out what the overall structure is. The diagram in the upper left-hand corner shows a mass spectra of a chemical called toluene, which is a common solvent. The peaks show places where molecular fragments are found. When molecules break down, they do it in predictable ways, and this helps the analyst understand what the overall structure of the molecule is. One of the problems you could have with a technique like this is contamination, when you're not working with a pure compound but actually have a mixture. The mass spectra will show the results of the mixture and let you figure out what peaks belong to what molecules. Fortunately, we have an excellent technique for separating mixtures, chromatography. The analyst can run the sample through a chromatograph and analyze each peak independently. This will give mass spectra for each peak, where each peak is a pure compound. Chromatographs and mass spectras are often sold as packaged systems controlled by a single computer system. Techniques such as mass spectrometry and infrared analysis can have extensive computing requirements beyond the fact that the instruments are controlled by the computer, a system that has to provide data acquisition, data display, perform calculations, and report the results. One of the major needs is library searching. When an analyst has a spectra for a chemical compound and has no idea what it is, they examine large compound libraries of spectra to get some idea what they're working with. Once these were housed in large volumes of books that people had to go through to get an idea what the structures were. Today these structures are all computerized, and the computer systems would do the searching for the analyst. This can take up a lot of bandwidth, not only in terms of computing, but because they are also accessing libraries of spectra that may be available from commercial, university, and government sources on the internet. There are other techniques that have similar requirements. Their names are listed on the screen. We're not going to go into them in any detail. The point is simply that these requirements exist, and if you're planning to support laboratory work, you should be aware of them. Instrumentation is being developed to provide an increasing capability to analyze both the structure and content of materials. In addition to the development of new methods, one of the trends is developing more complex instrument systems to provide better analysis. These are referred to as hyphenated techniques because they combine several techniques in series, one technique following the other, in the analysis of the same sample. The list on the screen shows some examples. The abbreviations for many of them you've already seen. GC for gas chromatography, LC for liquid chromatography, IR for infrared analysis, MS for mass spec, and a couple we haven't mentioned before. ICP stands for inductively coupled plasma. It's a technique for analyzing materials where we're looking for elements such as calcium, iron, phosphorus, sodium, and others. It's a very sensitive technique and has wide application across industries. NMR stands for nuclear magnetic resonance and is another spectroscopic technique that gives us information about the structure of molecules. One of the problems with these techniques, particularly those to the right of the hyphens, is that their usefulness will depend upon the purity of the samples being analyzed. Notice in these combinations of techniques the number of times chromatography pops up. Because chromatography is such a powerful separation technique, it solves a problem of providing pure materials to the next instrument in the series. In effect, we saw an example of this when we looked at mass spectroscopy. It provides another stage in preparing a sample for analysis. These combinations of techniques increase the demand for computers to control the instruments and collect data. Not all analysis techniques are used to determine chemical structures or composition. There are a number of methods that are used to measure physical properties of materials, such as thermal analysis. When you heat materials, a number of things can happen, the most common of which is melting and boiling. But there are other changes that can take place. You may have seen demonstrations where a very flexible piece of rubber is put into liquid nitrogen, removed, and then hit with a hammer, where it shatters like glass. That's because it's undergone a phase transition, referred to as a glass transition, where flexible materials become rigid and brittle. Being able to determine the temperature at which the glass transition temperature occurs, as well as being able to measure melting points of materials and how they crystallize, is an important part of materials characterization. That work is done using thermal analysis equipment. One such device is called a differential scanning calorimeter. When using the device, a sample is placed in the sample chamber, in this case the light-colored piece under the blue arm, and the temperature is slowly changed. The amount of heat flowing through the sample is measured and can be used to detect these phase transitions. The chart on the screen shows what happens to one material as it is warmed and goes through the glass transition, where it becomes softer and less brittle, then becomes a crystalline material, and then melts. The trace moves upward when crystallization takes place because the material often gives off heat when they crystallize and absorb heat when they melt. The purpose of the previous sections is to give you an understanding of the kinds of devices that scientists use in their work. This hasn't been an exhaustive treatment, but rather just gives you an idea of the kinds of systems that are available. In each of the cases, they all follow the same instrument workflow model: sample preparation, sample introduction to an instrument, followed by data acquisition and analysis by a computer system that might also provide a control function. Unless you're being asked to develop a computer system for a new type of instrument, most of your work is going to be focused on computer systems that provide analysis and control. The background information on the instruments themselves will enable you to talk to scientists about their work and better understand the problems they are trying to solve. If the scientist is working with a piece of equipment that you don't understand, ask about it. They are usually more than happy to talk about their work and help you understand what their needs are and help you support them. Before we leave the discussion about instrumentation, we would like to cover one technique that is widely used in life science industries, the ELISA assay. This technique is used to detect the presence of an antibody or antigen in a sample. This could be used as a screening test, for example, for HIV. This technique is a quantitative analysis method, one that looks at how much of the substance is present and uses visible light spectroscopy to make the measurement. It has benefited from the development of standardized test plates that can be used by a range of equipment from different manufacturers. The image on the screen shows a 96-well plate, one of the standard types of plates used in biological analysis. Each well contains a sample and in effect acts as an individual test tube. This arrangement allows a large number of samples to be processed simultaneously. In the example, we'll be testing for a particular antigen. The assay consists of a series of steps where materials are added, followed by wash steps until the process is completed. In the first step, we have a sample well that's been coated with an antigen that will react to the antibody we're looking for. The blue triangles represent the antigen that will bind to an antibody that might be present in the patient's blood serum. After the antigen has been added, excess material is washed out of the sample cell. In the second step, the patient's blood serum is added to the sample cell, and if there are any antibodies present, they will bind to the antigen. A second wash step removes any excess material. At this point, the antibodies are bound to the antigens in the sample cell. The material in the sample cell is semi-transparent. In order to complete the analysis and make the measurements, we have to develop a color whose intensity tells us how much, if any, antibodies were present in the sample serum. Step 3 involves the addition of an immunoglobulin coupled to an enzyme that will bind to the antibodies. After washing, the final step involves the addition of material that changes color when it is cleaved by an enzyme added in the previous step. If there are no antibodies in the serum, then enzyme will not be present and no color change will occur. After final wash, the intensity of the color is measured by a spectrophotometer and the analysis is completed. This slide shows a test plate where some of the sample cells show a reaction that indicates the presence of the antibody in the patient's serum. The deeper the green color, the more antibody is present. The plate is read by inserting it into a plate reader that is really a specialized spectrophotometer designed to read a specific wavelength of light and measure the intensity in each cell. This graphic shows a few of the cells and how they might be interpreted. Included with the analysis are control samples that are used to ensure that the procedure was done properly, in addition to cells that contain actual patient samples. This technique has benefited from different forms of automation because of the standardization of the cell plates. For example, instead of adding materials to each cell independently, groups of cells can have materials added using multi-channel liquid handlers, such as the one shown on the screen. Each tip is designed to work with one cell, and the spacing between the tips depends upon the number of cells on a plate. These tools would be used by a person. There are also systems that carry out the entire process robotically. Because of the standardization in cell plate format, equipment for handling the liquid additions, washers, readers, and plate stackers is available from a variety of vendors. The analyst can choose the best equipment to suit his needs without being concerned about whether or not it will fit the plates he or she is working on. Plates come in standard sizes with a fixed number of wells, and the equipment is designed to be compatible with these formats. Fully automated robotic systems are available to carry out the analysis. The slide on the screen shows one example from Caliper Life Sciences. This assay is another example of the implementation of the standardized instrument workflow model. During this session, we have looked at several different types of instruments for both chemical and physical property measurement. While the techniques can vary widely, they all follow the same model. Once you understand that model, you can readily apply it to techniques we haven't covered.